Alright, so today what we're going to do is we're going to basically cover in the rest of our time that we have, which is 30 minutes, we're going to cover about 3 weeks worth of Algebra 1, or about probably a good week's worth of Algebra 2. Alright, but you have seen this stuff before, we're just reviewing it pretty quickly, okay? So you're going to need to stay with me and really focus and get as much as you can out of this, alright? And start identifying areas where you may have forgotten things, okay? So you can supplement that. Alright, so we're dealing here with quadratic functions. We've actually finished chapter 1, we're into chapter 2 now. This whole unit, we're covering the first 2 chapters together. But we have 2 forms for our quadratic. We have the standard form, ax squared plus bx plus c. And then we have the vertex form, f of x equals a times x minus h squared plus k. Why is that called vertex form? Do you know?
Yeah,
What?
H is the vertex.
Okay, the h is part of the vertex.
Come on, Ben, come on. Ben's got it, Ben's got it.
H, comma, K?
Yeah, okay, it's the point hk. Alright, and where is that on our graph?
Where the blue line is, that point at the blue line, that red line.
Okay, good, it's that red point on the blue dotted line. Okay, that's our vertex hk. Alright? Yes?
Because it's x minus h, so is it h matter? If h is a negative number, to that time it should be positive.
Okay, that's a good question. Donald's pointing out something here. Think about your, because it's x minus h, that's the same way we had it when we were doing the transformations. The horizontal translation, it's the opposite of what it looked like. So if it was x plus 2, you were going to the left.
Yes.
And if it was x minus 2, you went to the right. So h, if it's x minus 2, h would be 2. If it's x plus 2, h would be negative 2. Okay? Very good observation. Alright? Now, since we mentioned this blue dotted line, what do we call this thing?
The bicep. Because this is the line of symmetry.
Starts with an A, that's right.
Asymptote.
No, it's not an asymptote, we hit it, right?
Yeah.
We hit the line, so it's not an asymptote. Notice it's, you're guessing the letters there. We're playing Wheel of Fortune. Alright. This side is identical to this side, right?
Symmetry, line of symmetry. I said it, a line of symmetry.
It's, well, but we call it the axis of symmetry. Okay?
Line of symmetry earlier.
It is a line of symmetry, but we call it the axis of symmetry. I want you guys to know the terms so you're not lost when I ask you to find it, okay? So the axis of symmetry. The axis of symmetry is always a vertical line, right? So its equation is going to be what? What's the equation of the axis of symmetry?
X equal to h.
Very good. X equals h. It always has to equal h because it's always got to hit the vertex, right? It's got to hit the vertex, so its x coordinate is h. Therefore, it's the line x equals h. All right? Now, what's that black point right here? What's that called? Y-intercept. There we go. Y-intercept. And how do we find the y-intercept? Very good. When x is 0. And by the way, that's true no matter what function we're dealing with. It's not just for quadratics. Okay? So there's our y-intercept. It's f of 0. So we're plugging in 0 for x. Okay? And then we had these green points here. And you're right, we can't call those x-intercepts. What's another term for those?
Zeros.
Zero.
Yes, those are called zeros. And why are they called zeros?
X equals 0.
Very good, because the function equals 0 there. F of x equals 0 at that point. 1? All right. So those are the basic terms that you need to know. There are 2 zeros. Yeah, both green points there. I kind of color-coded it for you. Okay? So a quadratic, listen, a quadratic will have up to 2 zeros. It's possible that a quadratic will only have 1 zero, like in our parent function. In the parent function, why does it only have 1 zero?
Because it always starts with origin.
So 0 is a 0.
Okay, 0, 0 is the 0.
F of x would only equal. Well,
It only equals 0 at one point.
yeah.
Because what is the 0? What other feature is that?
It's what?
The vertex. If the vertex is on the x-axis, then of course you're only going to have 1, 0. Alright, because the vertex is always your max or min point. Okay? It's also possible not to have any zeros. Okay, that would be a case like this. If I had my vertex up here and I went like this, or if my vertex were down here and it was opening downward, it was reflected downward, those would not have any zeros. Okay? So that is possible. Alright, but more often than not, we get 2 zeros. Okay? Alright, so now let's apply what we know about our transformations to some quadratics here. Let's go through these 4 first and identify the transformations, and then we'll take a look at what graph goes with which. Alright? So first of all, number 1 here, what's the transformation there?
Flip over the x.
2 units.
Excellent. It shifts to the right by 2 units. Very good. Okay? It shifts to the right 2 units. So I want to tell me number 2, 3 minus x squared.
With that by x-axis 8.
Okay?
And then up 3 units. Shift to the upper 3 units.
Good. It moved up 3 units, and it's also
With the x.
reflect across the x-axis. Okay, very good. Okay. Now, how about this third one? Someone else want to give us that one? Somebody who hasn't really told us anything today? All right.
So it goes up 3 units.
Okay, very good.
Very straight.
Shifted up 3 units. Okay, shifted up 3 units. And how about number 4? Grant?
Shifted 4 to the right and flipped over the x-axis.
Good, okay. 4 to the right, and it's reflected across the x-axis.
Isn't it the lot?
Okay? Notice the entire thing that's being squared is multiplied by the negative 1. If it were the y, then it would be a minus in here. Okay? Alright, so now we can match these here. So let's see, 1 goes with C. Okay? 1 goes with C. It's simply shifted over to the right 2 spaces. Okay? Number 2. Number 2 is D. It's shifted up 3. And notice it's opening downward. Alright, so good. Number 2 is D. Let's see here. Number 3. Number 3 is B. Okay, it's shifted up 3, but notice it's not reflected. So that's the difference there between number 2 and 3. It's not reflected. Okay, and then of course, number 4, process of elimination. But also because we see it is shifted to the right 4 units and it's reflected downward. So A is 4. Okay? Is there anyone who has a question about any of this before we move on? Okay, so that brings us to a process. This process is used for a few different things, okay? One thing that this is used for is getting from standard form to vertex form, converting from one form to the other, okay? It's sometimes helpful to get to vertex form because then we can see the transformations much easier, okay? Now, what process do you think we're talking about?
Factory.
If you haven't scrolled down yet.
Completing the square.
Completing the square. Good job. All right, we're going to complete the square. All right. Now, keep in mind what we're talking about here. We're giving a quadratic in a standard form like this, ax squared plus bx plus c equals 0. Okay, or equals f of x, either one. The square that we're trying to complete is a trinomial, okay? Kind of like x squared plus 6x plus 9. That's a perfect square trinomial because it factors into a binomial squared. All right? So what we're trying to do is we're trying to take whatever we're given and get it into a form that will factor into a binomial square. That's why it's called completing the square. All right? Sometimes students will work through this and they never really understand why it's even called that. Okay? Don't forget what our goal is, and that is to get something that's a binomial squared. Okay? So there's a process here. I'm going to run you through the process, keeping the A, B, and C first.
What is get A equal 1?
We'll get there. Okay? We'll get there. Let's run through it with the letters first, with the A, B, and C there. Then we'll look at it with numbers. Okay? So, the first step in our process, you'll notice I'm going to solve that equation that's set equal to 0 for x. Okay? So, the first thing we want to do is get that c to the other side. Well, I'm just going to subtract it from both sides. And I get ax squared plus bx equals a negative c. Alright, so that's pretty easy so far. The next step here that it says we want to do is we want to get a equal to 1. Now a is the coefficient of x squared. Okay? Right now the coefficient of x squared is a. So how do I get that to equal 1?
Plugging
No, divide the left side of the equation by a and take what you get, or take what you get from that outside. So put a outside, divide b by a, and have x squared plus b over ax in parentheses.
Okay, so you're saying factor 1 out,
Yeah, factor a out.
or just divide. We'll get it. We know a doesn't equal 0 because we're dealing with a quadratic. So you could do it either way. We'll do it this way for our purpose at this point. Okay? So we divide everything by a, and now we're left with the a's canceling out. So we have a 1x squared which is what we wanted, plus b over a x equals a negative c over a. Okay? All right, now here's the critical step, but it's one that you got to memorize. Okay?
B over
The b that we're talking about here, okay, is whatever the current coefficient of x is. All right? What is the current coefficient of x? It's not just b anymore,
1. Wait.
of x.
Shouldn't it be b over 2a squared?
No.
B over 2a
No.
squared at both sides?
What is the current coefficient of x that we have? It's b over a, all right? So, that's why I say here, when I say b in the little directions here, I'm talking about whatever it happens to be now, not necessarily the original one, okay? It's a little confusing, I get that, because we're still dealing with the variables, all right? Once you have all numbers, it's a little simpler, okay? So right now, the current coefficient is b over a. We got to divide that by 2 and square it, okay? Well, what's b over a divided by 2?
B over 2a.
b over 2a, okay? So I have b over 2a, and I've got to square that. So I now have b squared,
4a squared.
good, over 4a squared. All right? So we have b squared over 4a squared, and that is what I'm going to add to both sides. And guess what I did by doing that? I just completed the square. By doing this, will create a trinomial on the left side that will factor into a perfect square. Okay? So I'm going to add b squared over 4a squared here. And I'm going to add a b squared over 4a squared here. Okay? Now, the whole point in doing that is this, okay?
X plus b is.
The whatever we got right here, okay? When we go to factor that trinomial that we just ended up with, that trinomial will always factor into x plus whatever this was. So I'm going to put that b over 2a in here. All right? Does everyone follow what I've done here? I just factored this trinomial. It's a perfect square. It may not look like it. It may look really, really ugly. You may have all kinds of weird fractions or whatever in there. But the fact of the matter is, if you follow the process carefully, it will guaranteed factor into this. Okay?
Just like the simplified version of that.
Yes. Okay? Yes. So now, all we need to do is finish solving for x. Okay? Does everyone understand everything that we've done so far? I want to make sure we got that before we go any further. Because at this point, if we were graphing, we would just stop at this point. Because we've got it in vertex form. Okay?
Are you going to show us some numbers too?
Yes. Yeah.
I'm just confused where that yellow part came in.
The yellow part came in because I had this trinomial and I factored it into this x plus b over 2a squared. Okay? So your factor, okay, it'll always factor this way. Okay? Now, as we solve, you undo a square by square rooting. And when you square root an equation, you always have to do plus or minus. Okay? So you have b squared over 4a squared minus c over a.
And that would be equivalent to plus or minus b over 2a minus c over the square root of ac, right?
Not quite.
Oh.
I can't, since there's subtraction, I can't take the square root of one part minus the square root of the other part. I got to get it all into one fraction first. So what do I need here in my radical?
Multiplied by 4a. Oh, right.
Okay, good. I need a common denominator, right? So if I do a common denominator here, I'd multiply by 4a over 4a. There's another a to make that an a squared. Okay? And now I can do the square root of b squared minus 4ac over the square root of 4a squared, right? Once I have a common denominator and put it into one fraction, then we can square root the top and square root the bottom.
How do you go from the yellow to the purple?
I square rooted both sides to get rid of this square. Okay?
And then that would be plus or minus b.
Okay. Now, watch this. We subtract. We get a negative b over 2a plus or minus square root of b squared minus 4ac over,
This
Square
looks like
root.
2a.
That equals.
what, Sam?
Oh my god. B squared minus 4ac all divided by b. What is that called?
Yeah, I was gonna say, what is
Yeah.
that called?
This looks
Doesn't this look familiar?
Yeah, it's a quadratic. It's like a quadratic. Yeah.
It's the quadratic
Formula.
formula.
Gosh.
That isn't just some random thing some guy came up with, right?
Oh, snap.
These things come from somewhere. And it comes from a process that people do over and over and over and over and over again with numbers, and they recognize, why am I doing the same thing over and over and over again? So what they do is they plug in letters instead of numbers, and they come up with a formula. Okay? This is our quadratic formula. This is where it comes from. It comes from completing the square. Okay?
Steps.
So, okay? So guys, these things that you learn aren't just like made up, all right? They come from somewhere. And back in, Algebra 1, you probably learned this and they just said, hey, memorize it and do it. Okay? Now you're seeing where it comes from.
Well, I mean, technically they are made up.
Oh my god, Grant. I love you.
This is so.
So,
Yes.
how can you get from that part?
How do you get what part?
First, yes, the first
Do not say that in the
first part. Why do you like times 4a and also times 4b?
All right, here.
Yeah.
Because this is a 4a squared,
Yes.
I need a 4 and another a. So I multiplied by 4a over 4a to get a common denominator. That's how I was able to actually subtract and put them into one big fraction.
Oh, actually, you are telling 4a. Yeah.
Yes. Yeah. And then 4a times a is just 4a squared. Okay?
Induction, this is what it looks like.
Already passed induction.
Alrighty.
We have to do this
So-
next time.
Here's the thing. I know it's a little bit confusing with the letters. You're not going to have to reproduce this with all the variables in it. But I wanted you to see where it came from, okay? I want you to see where this comes from. You've used this 100 times before, the quadratic formula, but you probably had never seen where it came from, okay?
Even if it's x, how can we get the c?
Hang on, be quiet, please.
We get the x. this formula is for solving the.
Yes, this gets us what x is. So if I had the equation, 3x squared plus 5x minus 7 equals 0, I could solve it by just plugging in 3, 5, and negative 7 for A, B, and C.
But the thing is, we want to make the function to the vertex function. How to do this?
Yes, and that's what I'm going to do right now. This process is the same. And like I said, we would stop right here at the yellow step. If we were trying to get it to vertex form, we would stop here because it would be in vertex form at that point. I just wanted to show you the rest of the progression there all the way to the quadratic formula. Okay? So let's actually practice doing this. I'm actually going to do these in reverse order of what I have them listed. Okay? So let's look at 18. All right? This is in standard form. Okay, so in our process, notice we have an f of x. We're going to leave that f of x there, okay, because I want to be able to graph it at the end. We're not just finding zeros. We're actually going to graph this at the end. Okay, so what's the first step in our process?
Subtract c, so subtract 1 from both sides.
Okay, good. Get that 1 on the other side. So it's f of x minus 1 is a negative x squared minus 4x. Okay? Now what?
Get a to 1.
Make a equal 1. Alright? Right now a is a negative 1. So if I flip the signs, divide everything by negative 1, however you want to think about that. Okay, notice I've got to divide the f of x by negative 1 as well. So I get a negative f of x plus 1 equals x squared plus 4x. Okay? Now we've got to this step where you've got the step that you just have to memorize, basically. Okay? What are we going to add to both sides here?
B over 2.
B over 2. So right now B equals...
1.
No.
4.
B equals 4.
Yeah.
So I'm going to take the 4 over 2, and what am I going to do with that?
Square it.
Square it. And then that's what I'm going to add to both sides, right? So I'm adding a 4 over 2 squared, which happens to equal 4. So I've got to add it to the left side too. Got to be fair. Okay? So now I've got a negative f of x plus 5 equals an x squared plus 4x plus 4.
Complete the square.
The square has been completed, right?
Yeah. Yeah.
So now we have what?
Negative f of x plus 5 is equal to x plus 2 squared.
There we go. And we know it's x plus 2 because what did this equal? It equaled, before we squared it, it equaled a plus 2. Okay? So that's what goes in here automatically.
Sorry, why do you use that 2 becomes that 2?
This will factor into x plus 2 times x plus 2.
Yes.
Okay? So that's why now we're doing that. Because remember, our goal is to get it in that vertex form. F of x equals a times x minus h squared plus k.
Plus b 5.
Okay.
Or minus 5, right?
Well, watch this here. We now have to subtract 5. So negative f of x equals x plus 2 squared minus 5. However, you cannot leave this as a negative f of x.
By everything by negative 1.
Exactly. So we have f of x is a negative, watch this, it's still x plus 2 in the parentheses. The negative is on the outside. This is a plus 5 though. And now we can sketch it easily using our transformations. Alright, so at this point we have the parabola in vertex form, okay? And someone remind us here, what is the vertex then for this function?
-2, 5.
Yeah, -2, 5. Remember, the transformation, or the translation, I should say, of this one will tell us where the vertex is, okay? So it's at -2, 5, so -2, 5 right here is our vertex. And then what's the other transformation that we have?
It could be horizontally or vertically compressed or not. Oh, wait, never mind. Flip over the, what axis? X-axis?
Well, it is to the left 2 and it's up 5. That's why the vertex is there. Okay, it's reflected vertically across the x-axis, all right? So now, instead of being over 1 and up 1 and over 2 and up 4, we're going to find other points by going over 1 and down 1, over 2 and down 4, okay? And same thing to the left, over 1, down 1, over 2, and down 4, okay? So right here is a sketch of our parabola. Okay? But I want to identify some features here in this parabola. Okay? There are a few features that I want to make sure that we identify. So we've got the vertex. Let's consider here the y-intercept. Where's our y-intercept?
0.
At 0 something, right? So 0 what in this case? 1, okay? And remember, when it's given in standard form, that constant term at the end is always going to be your y-intercept. Okay? And you can see that right here on the graph. Alright, our y-intercept at 1. The other thing that we need to be able to find are the zeros, okay? The zeros of the function.
Plug it into the equation.
Okay? What are we going to plug into the equation?
The 0 into the y.
Okay, we're going to replace the y or replace the f of x with 0. Okay? So then we have to solve it. And, let's see, we'll do this over here. So we're going to have 0 equals a negative x plus 2 squared plus 5. By the way, you could do this using the original function as well. If you saw that that factored or something, you could go ahead and do that. This one's not going to factor. Alright? But actually, before we even solve, how do I know I'm going to have zeros?
For the parabola, just look at the...
You see it intercepts the...
Okay, we can see it's intersecting the x-axis, alright? Even if we hadn't drawn this yet, our vertex is above the x-axis, and since this is negative, we know it's going to be going downward, alright? So it's going to hit the x-axis. Okay? So at this point now, we'll go ahead and solve it. We're going to get negative 5 equals a negative x plus 2 squared. I'll multiply both sides by negative 1 to get rid of the negatives. Okay. Now what do we do? Square root both sides. So we've got plus or minus square root of 5 equals x plus 2. And then I subtract 2. So x is 2 plus or minus root 5. And root 5 is approximately 2.2. When you're graphing, you could go to the tenths place. Alright, so if that's 2.2...
Wait, why wouldn't it be minus 2?
Yeah, it's minus 2.
Okay.
So negative 2 plus 2.2 is going to be a 0.2. And negative 2 minus 2.2 is going to be a negative 4.2. Okay? So you can see here, here's that 0.20, and right here is the negative 4.20. Okay? And those make sense based on our drawing already. You know, we can make sure those answers make sense. Okay? Does that make everyone understand? Okay. Yes.
Why is a plus and a minus square root of 5?
Why is it plus or minus?
Yeah.
Anytime you're solving an equation and you've got something squared, if you square root, you have to consider both the positive and negative square root. Okay?
So if you drag that 5 to the left hand side, it should be minus 5.
Yes, but then I multiplied by a negative 1 because that was negative.
Oh, there's one negative?
There's a negative right there. Yeah.
Sorry.
It's okay. Okay? Now, one last feature I wanna look at here is our axis of symmetry. What's our axis of symmetry in this case?
The x equals -2.
X equals -2. Remember, the axis of symmetry is the vertical line going through our vertex. So our axis of symmetry is x equals -2. Okay? So those are all the key features there of the parabola. Now, one thing I will point out here, this is something that is worth memorizing, okay? Because sometimes we don't necessarily have to graph the entire thing. All we want really is the vertex. So going through the whole process of getting it into vertex form isn't absolutely necessary, okay? So one thing that can be useful to remember is that the h, when we're given the equation in this standard form, h is negative b over 2a. Okay? Now remember, yesterday we saw the quadratic formula. We derived that quadratic formula using completing the square. Okay? The easiest way to remember what h is it's the quadratic formula without the radical part, right? Negative b plus or minus the square root all over 2a. Well, we just got rid of the plus or minus the square root part. Okay? Well, once you know what h is, if you know the x coordinate of a point, how do you figure out the y coordinate?
Plug it in.
Plug it in. Okay? To get k, you're just going to find f of whatever you get for h.
So could you do it for this example?
Yeah, so for this one, my b is a -4, so h is a -4 over 2 times a. A is -1.
Wait, where'd you get -4? Oh.
Yep, we've got the minus here, so that's a -4. Okay? So now I know h is 4 over -2, which equals -2, which is the same thing we got when we had completed the square. Okay? So now, if I find f of -2,
Plug it in.
I get a negative times -2 squared minus 4 times -2 plus 1. So that's going to be a -4 plus 8 plus 1, which equals 5. Okay? So, that's the one thing that's going to be worth memorizing here, that negative b over 2a. You'll see why here in a little bit when we get to some application. Okay. All right, now, here's another one up here. It's already in vertex form. Take a moment and find your vertex, your axis of symmetry, your y-intercept, your zeros, and then use all of those to sketch it. Okay, so take a couple minutes here and work that out. Okay, so what's our vertex in this case?
6,3.
Okay, our vertex is 6, 3. So 1, 2, 3, 4, 5, 6, 1, 2, 3. There's our vertex. Okay, is there any other transformation on this? No. All right, so actually right now I could go ahead and sketch it. I know my parent function, I go over 1, up 1 from the vertex, over 2, up 4. I go to the left 1, up 1, and to the left 2, up 4. And I've got my parabola.
You just go over 3 on the second one. Oh, sorry.
Okay,
Sorry.
that's all right. Okay, so there's our vertex. What's our axis of symmetry? X equals 6, very good. Our y-intercept,
0,39.
f of 0, so it's 39, okay. If we plug in a 0 here, we get negative 6 squared, which is 36, plus 3 is 39, okay. And then what about our zeros?
No.
There are none, okay. Look at the picture,
Oh, I knew that.
okay.
Because I was getting eyes. I had a square root of -3.
Exactly. And that should tip you off, okay. And there are no zeros. But this is why I graph it as I go. As I figure stuff out, I graph it because that saves me the work. Alright? It didn't say solve for when it equals 0. It said find the zeros. If there are none and you can tell right away, you don't need to do any of that work. Okay? But you're right. You would find like the square root of -3 eventually there. And you can't graph that. Yes?
You know, like, every teacher so far has told me, like, you can't square root of negative. You can't root a negative by no rules, but they're like some sort of
It's
like.
imaginary numbers.
You can't and stay in the real numbers. You can't graph it on our normal XY plane.
Figure out like that.
There are imaginary numbers, and there is the Argon plane. Not Argon plane. That's a historical
I was like, I
thing.
don't know what that is.
What's that? Shoot. It sounds kind of like it. Anyways, there's a different plane where you have a real axis and you have imaginary axis.
Cool.
So you would graph numbers on that plane. Okay.
Chessboard where it's like 2 levels, so you're not even on the level.
So.
Why does it?
Alright, so there's a term that you need to know when it comes to applying quadratic functions, alright? And that is optimize, okay? And it's not just for quadratic, but we do a lot of this when we're working with quadratics. When we use the term optimize, that's just a word for finding the best solution. Now, best is kind of dependent on what your situation is, alright? If I'm playing golf, the best score is going to be the lowest one. However, if I'm playing football, the best score is going to be the highest one. So you have to think about the situation that you're in, okay? Either way, though, you're going to be finding max and min points, okay? So, just a few tips here. When you're working through a word problem, if you don't give you a function, you're going to need to try to write a function and think about the thing that you're trying to optimize. If I'm trying to find the best area or the greatest area, then my function is going to be the area equals something. If I'm trying to optimize my profits, if I'm in business and get the highest the highest profit. My function is going to be the profit in terms of x equals something. Okay? So write a function where the dependent variable is the value you want to optimize. Also, determine the domain. I like to call this kind of the situational domain, okay, or the logical domain. In a situation, you may not be allowed to have fractions for your answer. You may not allowed to have negatives for your answer, okay? Identify that at the beginning, okay? For example, if we're talking about, how high a ball is off the ground, we're not going to be having negatives, okay? So, there's a case where we have to consider the domain. So finally, we're going to look for the max or min point inside that domain to find our optimal solution. And that means we're finding what with the quadratic? The vertex, okay? We're finding the vertex. Okay? Once you understand that, a lot of these problems are pretty simple overall. Okay? Let's look at one here. Here it says an indoor physical fitness room consists of a rectangular region with a semicircle on each end. The perimeter of the room is to be a 200-meter single-lane running track. Okay? So let's write down what we're given already. Okay? So my perimeter is 200 meters. And this is kind of going into part A. Alright, it says we're going to draw a diagram and we're going to let x be the length and y be the width of the rectangular region. So here's our diagram. We've got this rectangular part and they said let this be x and this be y. But then they said that there is a semicircle on either end. Okay, if you look out the window, you'll see the track. So this is kind of what we're making here, except it's only 200 meters instead of 400 meters. Okay? Now, at this point, it's kind of stepping us through how to get the rest of this. I want to do part B, okay? And then I'm going to let you guys work on C, D, and E for a minute here and see if you can come up with that yourself. Part B, it says, determine the radius of the semicircular ends of the track. What's the radius?
Half of a circle. 1/2 y.
Is it y?
Okay, it's half of y, alright? So our radius here, I'm going to draw a radius. R is half of y, so I'll just put y over 2 there. Okay, there's our radius. Now, it says here, determine the distance in terms of y around the inside edge of the two semicircular parts of the track.
What do you mean, like the circumference? Is that what it's asking for?
Well, it's asking us for the distance around the two semicircular parts. Well, if I have two semicircular parts, what do I have? I have a full circumference, right? So how do I find circumference?
Pi r squared. What am
No.
I saying? That's it. I'm asking.
2 pi r. Okay. So circumference is 2 pi r. And I know now that r is y over 2, right?
Pi y.
Pi y. Y pi.
That's right. Okay, so the 2's cancel out, and I have pi y. Okay?
Y pi.
Now, I'm going to give you some time here. I want you to work through C, D, and E. Go ahead and work with somebody and see if you can't finish this off here. To find a rectangle with maximum area. We want to make it 200 meters all the way around, but we want to have the most space in the middle so it's actually useful, okay? If we're making this inside a physical fitness room, we could maybe put all of our other workout machines in the middle, all right? So let's figure out how to make that space the biggest possible. All right, so part C, you wanted to write an equation for the distance traveled in one full lap, right? So you had this pi y for the circular parts plus the two x's. And we were told that that's supposed to be 200. Okay? That's 200. So now we subtract the 2x from both sides, we divide everything by pi, and we get y equal to 200 minus 2x all over pi. Are there any questions about how we get to this? A lot of you had gotten here, but I just want to make sure all of us are here.
Yeah.
Okay? Alright, so now it says use the result of part C to write the area of the rectangular region as a function of x. Well, here's the rectangular region. Area of a rectangle is length times width, which happens to be x times y. So if we're going to write the area as a function of x, we need to have x times y in terms of x. Okay? So we have 200 minus 2x all over pi. Now we have a function for our area. And now, notice if we multiply by the x, if we distribute that in, we're going to have a quadratic. Okay? We're going to have a quadratic. And this is what part E was trying to get you to do. We could graph that. Okay? We could even do it without the graphing calculator here. Let's take a quick look at this without the graphing calculator. Okay? I'm going to split this into two separate fractions and distribute the x in. Okay? So my a of x I'm going to rewrite as 200 over pi times x minus 2 over pi times x squared. Okay? Now the reason why I did this is because if we want the maximum area, I need to find the vertex, right? What form is this in? Is this in vertex form? No. Okay, so this is where, remember I told you it's helpful if you remember h is a negative b over 2a. Okay? Remember b is the coefficient of x.
200 over pi?
Yeah, so we got a negative 200 over pi over 2 times the coefficient of x squared. A is always the coefficient of x squared.
Why is it a negative 200 over pi? Why not just a 200 over pi?
Because it's negative.
B.
Remember the negative b part?
Oh, my bad.
Okay, yeah, the negative b. Alright, so now we have here the negatives canceling. We have 200 over pi over 4 over pi. The over pi's cancel out, and 200 over 4 is 50. So 50 meters is going to be the length of our side. Okay?
That's your x.
That's our x. Alright? So to get the maximum area, we want x to be 50. And that maximum area is going to be a of 50. Okay? So if I plug in 50, I get 50 times 200 minus 2 times 50 is 100 all over pi. So that's going to be 50 times 100, 5,000 over pi square meters. Okay? Which at this point, now you could go ahead and divide by the value of pi to get a number that makes sense to us. Okay? So that's going to be what, like 1,600 something?
Why we ask for vertex?
I'm sorry, what?
What we want a maximum, what we do the vertex?
We wanted the maximum, so we get the vertex, okay? Because on the parabola, look at this, at our function, it's going to be a parabola that looks like this. Because see the negative in front of the x squared? It's going to be opening downward,
Okay, yes.
okay?
1,591.
1,591?
Yeah.
Okay. So, 1,591 square meters. That's going to be our maximum amount of area that we can include. Okay? So now, if we build it this way, we can also now buy equipment that'll fit into that space. You know, if we wanted to make that like the workout area and have the running track going around it, okay, we can do that. What? All right, so let's look at a different type of question. All right, here we have projectile motion. All right, our projectile is a person jumping off of a diving board. Okay, so here he's jumping off of a diving board. He goes up and comes back down into the water. Okay, so it says the path of a diver is approximated by y equals negative 4/9 x squared plus 24/9 x plus 12, where y is the height in feet and x is the horizontal distance in feet from the end of the diving board. Alright, so check this out. It's saying x is the horizontal distance from the end of the diving board. So here's our y-axis right there. And where is our x-axis going to be?
On the board itself. Oh, wait.
Look at our model. What's our y-intercept in our model? 12. So this right here must be the point 0, 12, right?
Yeah.
So where must our height be measured from?
The bottom, the pool water.
Yeah, the water, okay? So, there's our x-axis, and there is our y-axis, okay? So, go ahead and find the maximum height of the diver. How would we find the maximum height of the diver?
Negative b over 2.
Yeah, the vertex, negative b over 2a. Okay? So, we're trying to find this point right here, HK. Alright, so H is negative b over 2a. What's b?
Negative 24 over 9.
Good, okay, we got 24 over 9, so negative 24 over 9 over 2a. What's a?
Negative 4 9.
A is a negative 4/9, so it's a negative 2 times that. So 2 times 4/9 would be 8/9. Okay? And what does that equal?
3.
3. So guess what? It's going to occur when we are 3 feet away from the end of the diving board horizontally. Okay? That's where it's going to occur. Now we just need to know how high. Okay? So what do you get if you plug in 3?
16.
You got 16? Okay. So you plug in 3, that's 9, cancels with the 9, so that's a negative 4. 3 cancels with 9, leaves 3, so 24 over 3 is 8. So I've got a negative 4, plus 8 is 5, or plus 8 is 4, plus 12 is 16 feet. Good, good. So the maximum height is 16 feet off the water.
The hardest thing about this is like taking apart the question.
You're right. You're right. The hardest part of most word problems is not the mathematics. It's getting from the situation to the mathematics. All right? So you got to read carefully. You got to try to interpret things in terms of what we're talking about. Okay?
Wait,